Hello. So today we are going to consider an estimation problem which you will see every 4 years, once every 4 years. So this is about the presidential election prediction. And let's start with this graph, which is a real graph, like took from CNN, actually like nearly 10 years ago. At that time, maybe this is the second term election for President Obama. And what I want you to focus on here is simply just percentage. We would like to estimate the percentage of votes for Obama. And here, margin of error is plus minus 3.5% points. So this margin of error is exactly the margin of error uh, we uh, we learned in this chapter. And sample size is 783 likely voters. So this is the sample size. Sample size we learned. Exactly we are this I will show you at the end of this slide that I will show you how CNN calculated this prediction. And even if it's not shown here, the confidence level is 95%, which is the standard confidence level. So I think that's why it's not explicit on this graph. And what I want you to think about is, so think about the sample size, 783. If you do not understand the statistics, you may think this number is weird. Like say, I would ask, say, usually the survey goes out to say 1,000 people or like 2,000 or 500. It's not a clean number. It's an unnatural somehow. It's not another some strange number. How did they get this sample size? I will derive. It's not an accident like a ad hoc number, but it's deliberately chosen number. So it's not just by accident, right? It is the result of a careful design of the survey. So we are going to study how this result was obtained. That's the last example from this chapter. So think about this. First, we have to think about the underlying distribution. This is a very special case. I am going to so remember the sampling distribution is about multiple observations, but underlying that is a single outcome distribution. In this case, what you are doing is an experiment is a survey, surveying 783 voters. Sampling 783 voters is one experiment. So you observe 783 outcomes at the same time, once in one experiment. But even deeper, what the underlying distribution is a binary distribution. So simply, I will consider I will simplify the situation so that I will ask, do you support Obama or not? Let me simply so, do you support candidate A or not? So this I will put it this way. So if yes, I will encode it as 1. If not, 0. So it's yes or no question. So simplify. I will for a while I will ignore other smaller parties, and then on if you understand this underlying distribution is a binary distribution, then you can consider what parameter the relationship between the parameters. Say we are interested in the percentage of voters supporting this candidate, say Obama, and the parameter can be defined in this way: P, which is probability that x equals to 1. This is what we want to estimate. So what we want to estimate, if you ask all voters, then what is the probability of supporting Obama? And remember, it is one of the most important properties of a binary distribution. Probability of success equals the mean, right? So at that time, I told you mean doesn't mean anything in a binary distribution, but probability is a more natural interpretation. However, it is nice to know this relationship because all the methods that can be applied to the mean is now applicable to the probability. Because the probability is the mean, you may use, say, interval estimation theory for the mean to the estimation of probability. For example, we learned the best estimator for the population mean is the sample average. Sample average is the best estimator for the true mean. Then because the probability is the mean, now you can say this. The sample probability is the best estimator for the true probability, right? So, I'm using this equality to borrow the framework, the methods for the estimation method for the mean to our example. And then there is another thing you need to remember is that the standard deviation. The standard deviation of binary distribution is given by this. So variance is the multiplication of probability of success and probability of failure. And standard deviation need to take square root of that. And then what's strange here is standard deviation does not need to be calculated separately, but it depends again on p. It depends on p again. So this relationship will be used again later, right? Okay. And then let's think about a more simple and concrete numerical example. We are going to construct a 95% confidence interval for the true probability of supporting the candidate. And simply, I will assume 400 voters. Survey has been done on 400 voters, and among 400, 320 said yes. So it's a fake example. Simply, then in this case, from this information, can we construct a confidence interval? Yes, we can. Let's see. First, so remember, we need 4 things to construct the confidence interval. First, sample mean. Sample mean in binary distribution equals sample probability of success because mean equals probability of success. So in your sample, out of 400 voters, 320 said yes. 320 had success, which is 0.8, 80%. So the sample mean is 80%, which is the sample probability, 0.8. And second, so the sample mean, sample average is calculated, and then standard deviation can be calculated using the formula again. Standard deviation is square root of p times 1 minus p. And p is calculated here. P, sample probability, 0.8. Plug in and calculate. Use calculator. Then you get 0.4. So standard deviation can be calculated from this formula. And we got 2 of the 4 components. And then sample size, straightforward. Just in case, square root of 400 is 20. And 95% confidence level implies 2.5 top 2.5% value from the standard normal distribution, which is 1.96. Remember, plus minus 1.96 contains 95%. That's what we learned here earlier. And then, given those numbers, we are good. You can just calculate the marginal error. we learned it's 1.96, standard deviation 0.4, square root of n20. Just plug in and calculate. And then point estimator was 0.8. So from this, add and subtract the marginal error. You get this. This is how you obtain the confidence interval for 95%. So the parameter P, the probability of supporting the candidate, is estimated to be somewhere in between approximately 76% up to 83%, 84% approximately. So this is how we apply the same theory to presidential election prediction, right? And then we may so by the way, if you look at these numbers, the marginal error may be too large. Marginal error is currently 3.92% point. 3.92% is the marginal error, but you'd like to reduce the marginal error to 3.5%. So earlier it was too large, so let's reduce it to 3.5. Then you can calculate the required sample size to have this without changing the confidence level. And then, as you see, the z value does not change, still 1.96. Standard deviation does not change, 0.4, but the sample size should change. Instead, this guy should be smaller than the desired marginal error, 0.035. Rearranging this inequality, we have this inequality at the end. So n should be greater than 501.7 something. So n list, you should have 502 observations. So you need 502 observations to reduce the marginal error to this level, to this much. That's what we learned, and we are applying the same thing. So as you see, application is pretty simple, right? It's a very simple algebra. So just like do the homework and make yourself familiar with the application and the algebra. That's all, right? And then so then let's consider this poll. Another numerical example for your exercise. So you surveyed 400 voters, and 200 of them supported the candidate, right? And we would like to find the marginal error. So like basically it's constructing the confidence interval is equivalent to calculating the marginal error, which will be added and subtracted from the sample mean. So calculate the marginal error with these numbers. Same structure, so you can use the earlier example and try in a similar way. I'm going to show you the answer in the next video. So see you there.